Hi, welcome to the last presentation of circuits elements. In this presentation we will talk about RC circuits, resistance, capacitance circuits. So this is a very simple RC circuit. You have a capacitor connected in series with a resistor to a battery. Now there is a switch there that is open, and let's say that the capacitor is initially on charge, so there is no charge on the capacitor. Now if we analyze this situation in which I call it T before, that is before closing the switch, so what happened with the potential difference across the elements of the circuit? So the charge, we said before, the charge is zero because the capacitor is not charged. If the charge is zero, that means the potential difference across the capacitor, that is equal to the charge divided by the capacitance, is zero because the charge is zero. Now we know that if the switch is open, then there is no current through the circuit. That means the current is equal to zero. If there is no current to the resistor, then the potential difference across the resistor equals zero because the current is zero. So up to now we know that the potential difference across the capacitor is zero, the potential difference across the resistors, this resistor is zero. So what happened with the potential? Well, let's say this is the low potential, and we are going to call it B equal to zero. So this is our reference. The potential is zero here. Now, because this is a battery, the potential difference should be epsilon. So if this is low potential and we are saying this is zero, this should be high potential, this is positive epsilon. Now, because this end of the battery is directly connected to the resistance, this end of the resistor should be zero. That's the reference, you see. Now, because we know the potential difference across the resistor is zero, that means the potential difference is zero. If this is zero, this is zero too. Now this is our ideal wire, so that means this is zero. The potential here is zero. Now we know the potential difference across the capacitor is zero. That means this point is a zero potential too. This point should be a zero potential because that's the same. Now in this part here, the potential is positive epsilon, then should be positive epsilon because this is the same wire, is directly connected. So you see in this circuit, before closing the switch, the potential difference across the resistor, the potential difference of the battery is not on the resistor, is not on the capacitor, it is on the switch. And that's why when you close a switch, there are sparks here, electrical sparks, because the potential difference is here. Now what happens when you close the switch? If you close the switch, let's say just at the time you close the switch, the switch is already closed, but just at the time the switch is closed, the charge of the capacitor is almost zero. If the charge in the capacitor is almost zero, that means the potential difference across the capacitor is almost zero. The potential difference across the switch is zero because it's now closed. So that means if we analyze the circuit, so if this is reference zero, then this is positive epsilon because this is high potential. This is zero because it's directly connected, you see. In this case it's zero because it's directly connected. Now because we know the potential difference across the switch is zero, that means this is epsilon, this is epsilon, and because the charge on the capacitor is almost zero, the potential difference is almost zero, that means this is epsilon, and you see this will be epsilon. That means the potential difference across the resistor is now the voltage of the battery, and because of that then there will be a current. So because we know the potential difference across the resistor is epsilon, and according to Ohm's law is Ri, we can isolate, and the current through the resistor is epsilon over R. That means there is a current in this direction, and that current is the same as the current through the battery. So just at the time you close the switch, there will be a current, a big current, that is epsilon over the resistance. Now what happens when the time goes? let's say that the time goes a little bit, there is a charge on the capacitor, the current through the resistor will charge the capacitor. Now let's say we are some time after the switch is closed, the charge will increase on the capacitor. That means the potential difference will increase, will be difference from zero, it will increase. The potential here should be zero. I mean, we take that as a reference is zero. Then the potential here will be positive epsilon. The potential here will be zero because it's directly connected to the zero reference. The potential here, because this is directly connected, remember this is the closest, the switch is closed, this is directly connected, so that means this is positive epsilon. We know that the potential difference across the capacitor is not zero, but it is greater than zero. So let's say is, let's say is epsilon over naught, the half of the voltage of the battery. That means this will be the potential epsilon over naught over 2, and because this is directly connected, it should be this part of the resistor epsilon over 2. So that means the potential difference across the resistor will be half of epsilon, and the potential difference across the capacitor should be half of epsilon. That makes sense because you know that the potential difference of R, the voltage of R, plus the voltage of the capacitor should be equal to the voltage of the battery. So that makes sense. I mean, there will be some time that the voltage of the capacitor should be the voltage of the battery divided by 2. So the potential difference across the resistor should be epsilon or naught, and then you will have a current. And you see that current that is going through the resistor is less than before. So that means when you initially close the switch, you will have a high current that is epsilon over R. But now, when the time goes, this current will be decreasing, and the capacitor will be charging more and more and more. You see, the potential difference across the resistor plus the capacitor equals the potential difference across the battery. And because the potential difference across the capacitor is increasing, that means the potential difference across the resistor should be decreasing. And that will end sometime. So what happens when the time is greater than 0? So long time has gone. Long time has gone, that means the potential difference across the capacitor should increase and the potential difference across the resistor should decrease up to 0 because there will be no current. So the capacitor will be fully charged. Fully charged means that the current through the capacitor is 0. So the current on the circuit should be 0. If the current on the circuit is 0, that means the potential difference across the resistor is 0. If the potential difference across the resistor is 0, then the sum should be the potential difference across the battery. Then the potential difference across the capacitor should be the battery. And that let's see what happens with the analysis of the potentials. Reference 0, positive epsilon. This is 0. This is positive epsilon because it's directly connected here. And then this is 0 because there is no current, so I mean the potential difference across the resistor should be 0. And if this is 0, then this should be 0. You see, the potential difference across the capacitor is epsilon, the voltage of the battery. And that makes sense because the voltage of R plus voltage of C should be equal to the voltage of the battery. And the potential difference or voltage of R is 0. So that means the voltage of the capacitor is the battery. But that's long time after the switch is closed. There you go. The potential difference across the capacitor should be epsilon. And with that we can calculate the charge on the capacitor. That's just the capacitance multiplied by the voltage. Now a more complicated circuit. So let's see this circuit. In this circuit you have the capacitor is connected in parallel with the resistor 1, and then both of them are connected in series with resistor 2, and there is a switch. So before closing the switch, let's say the capacitor is on charge. If the capacitor is on charge, the charge is 0. So that means the potential difference across the capacitor is 0. If the potential difference across the capacitor is 0, that means the potential difference across resistor 1 should be 0. Because they are connected in parallel, you see they are connected to the same points, directly together. So that means the voltage across R1 is 0. Now, because this switch is open, there is no current, so there is no current through R2. That means the potential difference across R2 should be 0 too. Now, and the potential difference across the switch is epsilon, as we said before. Now, what happens just after the switch is closed? Just after the switch is closed, we know that the charge on the capacitor is almost zero, and that means the potential difference across the capacitor should be zero. You see, because it's on charge, right? It's starting to charge, but there is no charge now. So that means the potential difference is zero. And because the potential difference across the capacitor is zero, then the potential difference across R1 is zero, and because they are connected in parallel. If that happens, that means the current through the battery, because now there is current, will go through the capacitor and then through R2. There is no current through R1 because there is no voltage in R1, so it cannot have current. So the current goes through the capacitor and through R2. And you see, in this case, it's just like having one resistor. So in this case, the potential difference across R2 should be epsilon, and the current through R2 should be epsilon over R2, and the current through the battery is the same, epsilon over R2. So that's the analysis just after the switch is closed. Now, what happens when some time has gone? You see, because the current is going through the capacitor, the capacitor starts charging, and that means the potential difference across the capacitor starts increasing. And because the potential difference across the capacitor plus the potential difference across R2 should be equal to the battery, then the potential difference across R2 should be decreasing. And also because the capacitor is in parallel with R1, if the potential difference across the capacitor increases, then the potential difference across R1 increases. So we can say that the voltage of R1 plus voltage of R2 equals the battery, or the voltage of the capacitor plus the voltage of R2 equals the battery. Now, the charge starts increasing, so it's different from zero. Now the potential difference across the capacitor is greater than zero, and the potential difference across R1 is greater than zero and actually equal to the potential difference of the capacitor. Now, in this case, in this middle time case, you will have a current through the capacitor and a current through R1, and the sum of these two currents is the current through R2. Now, it's difficult to calculate the current. We know that, as we said, that the voltage of R1 plus the voltage of R2 equals the battery. Now, what happens a long time after the switch is closed? A long time after the switch is closed means that the current through the capacitor is zero. There is no current through. Why? Because the capacitor is fully charged. So all the current is going through R1 and then through R2. So there is nothing through the capacitor. That's important. So that's when you say the capacitor is fully charged, is because there is no current through the capacitor. Now, the current through the capacitor is zero. That means that the current through R1 plus the current through R1 is equal to the current through R2 equal to the current through the battery. Now, that's the current through R1 and that's the current through R2. Those are the same, and the same through the battery. So the current through the battery is epsilon over R1 plus R2, right? And we also have that the potential difference across R1 plus the potential difference across R2 equals the battery. Now, if the resistors are the same, the resistance of the resistors are the same, then the current to the battery is just epsilon divided by 2R, because it's like having two resistors in series. This is not playing a role, right? The capacitor is not playing a role. The current is going through the resistor 1 and then through resistor 2. Now, what happened with the voltage of the capacitor? The voltage of the capacitor is always equal to the voltage of R1. If they are equal, the resistances are equal, the voltage of R1 should be half of the voltage of the battery. So that means the voltage of the capacitor should be half of the battery. And that's what we said. The voltage of the capacitor is the voltage of the R1, and if they are equal, right, because we're saying here that they are equal to resistances, then the voltage of the capacitor equals the voltage of the battery over 2. So pay attention to that. When the capacitor is fully charged, doesn't mean that it has the voltage of the battery. No, the final voltage of the capacitor depends how it's connected. So that is important. Thank you. this is the last presentation of circuit elements.